Hello everyone, welcome to Physics Academy. This is our part 5 for Jest 2024 PIQC solutions, and in this section I will discuss part B, 3 marks MCQ questions. Okay, so in the previous videos I discussed 5 questions. I have discussed 5 questions for part B 3 marks questions. In that video, in today's video, again I will discuss another 5 questions. So 6 to 10. Question number 6 to question number 10. Okay. So myself, Mishun Patro, I am a PhD scholar at NISR ACPS. I am actually working in exoplanet atmosphere and exoplanet formations study. Okay, so let's start our lecture today. This is our question number 6. Okay, this is our question number 6. Question 1 to question number 5 we already discussed in part 4. Okay, in part 4. So this is part 5 for part B, part 5 for Jest 2024 solution series. Okay, so the question is, what is the questions actually? Basically, consider a particle of mass m moving in a three-dimensional delta potential V of r is equals to alpha delta cube of r, where alpha is the positive constant. Which of the following is allowed expressions for the energy of bound state for some dimensionless proportionality constant beta, and beta is greater than 0. Okay, so actually here given potential, right? Here given potential, three-dimensional delta potential, and delta potential, and this potential is depends on only r coordinate, so it is spherically symmetric potential. Okay, so this is spherically symmetric potential. So we know if I have potential, then how to calculate the energy. Okay, so from potential to calculate energy we use the Schrodinger equations, right? So here the dimension, the three-dimensional delta potential is given. Okay, and now the Schrodinger equations for particle in this potential, for this delta potential, minus h cut square upon 2m grad square psi r minus delta cube of r psi r and e psi r, where e is less than 0 because for bound state, because we calculate the energy for bound state, and for bound state energy always less than 0. So in spherical polar coordinate system, the Laplacian operator is nothing but 1 by r square del r square del psi by del r. So let's substitute this. So that is equals to minus h cut square upon 2m 1 by r square del r square del psi by del r minus alpha delta cube of r psi r e psi r. Okay, this is actually Schrodinger equation for spherical coordinate system. Now here given some boundary conditions. Okay, so for boundary conditions for this potential, actually the delta potential is singular at r equals to 0. Okay, this means, what is the meaning of that? The delta potential is obviously singular at r equals to 0, right? Here given a delta potential, actually here given a delta potential, and this is the value of r equals to 0, and here r equals to plus infinity, here r equals to minus infinity, and this is nothing but a delta cube of r. This is the potential, this is the given potential. Okay, and this potential is singular at r equals to 0. Obviously it's singular. It means the wave functions must be satisfy continuity conditions at r equals to 0. Okay, the wave functions must be satisfy the continuity conditions at r equals to 0, and the derivative of these wave functions will have a discontinuity, obviously discontinuity, due to the delta functions. So due to when this kind of potential is given, there is potential given, then two boundary conditions actually arise. At r equals to 0, the wave function must be continuous, and the derivative of these wave functions have a discontinuity at r equals to 0. Okay, So now we calculate the derivative. First of all, we calculate the derivative at r equals to 0. Derivative. So we know the derivative of this psi of r, it means we just integrations of the Schrodinger equations. Okay, if we calculate the derivative of psi of r, then we calculate the integrations of Schrodinger equations. So now the integrations of Schrodinger equations, minus h cut square upon 2m, 0 to psi for some small quantity grad square psi of r delta cube of r minus alpha psi of 0, minus alpha psi of alpha is a constant value. Okay, don't worry about alpha. So now this is equals to minus is handward to right hand side. So h cut square upon 2m del psi upon del r tends to 0 plus is equals to alpha minus alpha psi of 0. So this is equals to del psi upon del r tends to 0 plus r tends to 0 plus the discontinuity is equals to r tends to 0 plus is equals to minus 2m alpha upon h cut square psi of 0. So this is equals to del psi upon, this is the continuity value at r equals to 0 plus, the first derivative. Okay, so this is equals to del psi upon del r at r tends to 0 plus equals to minus k of psi of 0, where k is nothing but plus 2m alpha upon h cut square. Okay, we just calculate the derivative of these functions. Okay, there is this kind, there is a value, this value, the amount of discontinuities actually arise at r equals to 0. Okay, now we have the functions, wave functions for spherically symmetric potential. We know the wave functions for spherically symmetric potential, that is equals to psi of r proportional to e to the minus k of r upon r, where k is nothing but root under minus 2m e upon h cut square, where minus because for bound state. Okay, now find from these expressions the energy value, that is equals to squaring both sides, h cut square k square upon 2m equals to e. So e equals to minus h cut square k square upon 2m. Okay, so now minus h cut square upon 2m into, let's substitute here the value of k, okay, plus 2m alpha upon h cut square. So that is equals to minus h cut square upon 2m 4m square alpha square upon h cut to the power 4. So finally we get minus 2m alpha square upon h cut square, so let's consider 2 is a constant, so that is equals to beta m alpha square upon 2h cut square. So option C is the correct answer. Okay, so option C is the correct answer. Okay, so this is very easy questions, just note down and understand myself. Okay, next go to the question number 7. A particle with energy greater than 0 is incident from the right on a one-dimensional potential composed of a delta potential barrier at x equals to 0 and a hard wall at x equals to minus a. Okay, at hard wall at x equals to minus a. So this is the x equals to 0 and this is the point x equals to minus a. So there have a some hard wall, infinite potential wall. Okay, infinite potential wall, this is the infinite potential wall at x equals to minus a and less than x equals to minus a, and there have a delta potential as like that. There have a delta potential. Okay, they have a delta potential for alpha delta of x equals to 0, delta of x. Okay, this is the one kind of potential. This is hard potential, and this is delta potential. Okay, delta potential. Alpha is greater than 0, a is greater than 0. Let's define k square equals to minus 2me upon h cut square, and the dimensionless quantity zeta equals to ka and beta equals to h cut square upon 2m alpha a. Okay, these are the some constant. For some energy E, the particle, for some energy E, some particle reflect from the barrier without any phase shift. Okay, that's a very important point. Some energy, when a particle incident on a barrier with energy E, and at some energy particle reflect from the barriers without any phase shift. That's very important. Which of the following transcendental equations determine this energy? Determine this energy E. Note that in the presence of this delta functions barrier, the derivative of the wave functions has a discontinuity at x equals to 0. So it's have a value already given. Okay, it's a value. So we use one by one point. So here the potential is defined as v of x equals to alpha delta x. X is greater than minus of a, and v of x equals to infinity at x less than minus of a. This is the hard potential and this is the delta potential. Okay, this is given. A particle, okay, a particle with energy E greater than 0 is incident from the right of x greater than 0. Incident from the right from x greater than 0, and its wave functions reflect without any phase shift, and its wave functions reflects without any phase shifts, which basically mentioned in the questions. Okay, so now the Schrodinger equations of that particles, which particles have energy E greater than 0, is equals to minus h car square upon 2m d2 psi upon dx square plus v of x equals to e psi of x. Now we find these general solutions for two cases. One for x greater than 0, and another is minus a. So we just plot here the potential barrier. We just plot here the potential barrier. Okay, so of a delta functions of barrier at x equals to 0, delta functions of barrier at x equals to 0, and that is equals to x equals to minus a. Okay, this is the kind of potential. So we have find the general solutions for x greater than 0 and minus a greater than x less than 0. So there have a two, we find these two regions. This is the region 1, x greater than 0, and this is the another regions. This is the another region, region 2, minus a greater than x greater than less than 0. Okay, these two are regions. We're trying to find out the solutions of the function when particle incident from right hand side with energy E, when with energy E, sorry, greater than 0. Okay, this is the case. So for x greater than 0, this is the free regions. X greater than 0, this is the free regions. For these free regions, we have the Schrodinger equations minus h cut square upon 2m d2 psi upon dx square equals to e psi of x. So from these solutions, we have the from these Schrodinger equations, we have the solutions like that. Okay, psi of x equals to a to the power ikx plus b to the minus b to the power minus ikx, where k is the root under 2me upon h cut square. This is very easy questions, we already know, right? So if you just simplify it, that is equals to d2 psi upon dx square minus 2me upon h cut square psi of x. So this is equals to d2 psi upon dx square plus 2me upon h cut square psi of x equals to 0. So this is equals to d2 psi upon dx square k square psi of x equals to 0, where k is nothing but 2me upon x square, 2me upon h cat square. And when find out the solutions of these equations, we get psi of x equals to a e to the power ikx plus b minus b e to the power minus ikx. Okay. Now for these regions minus x minus a less than x less than 0, minus a less than x less than 0, also a free regions. Okay, also for a free regions. So for these free regions we have find out the solutions. Minus h cat square upon 2m d2 psi of x upon dx square equals to e psi of x. And in a similar way we find out the solutions, and we use the boundary conditions also at x equals to minus a, at x equals to 0. Then you get a solutions that is equals to psi of x equals to e c sin kx minus a. But how? We know the hard wall boundary conditions. For delta potential for hard wall boundary conditions is at x equals to minus a. It means at that point wave function must be vanish. Hard wall boundary conditions means at that point x equals to minus a, the wave function must be vanish. So psi of x minus a equals to 0, obviously. So we have now wave functions psi of x equals to c sin k x plus a. Now we find out the value of the wave function at x equals to minus a. X equals to minus a. So this is equals to c sin k minus a plus a. That is equals to c sin k into 0. That is equals to c sin 0. That is equals to 0. Okay, wave function must be vanished. Wave function must be vanished at x equals to minus a. So the solutions for minus a less than x less than 0 becomes psi of x equals to c sin k x plus a. This is the solutions. Because it satisfies the boundary conditions. These solutions satisfy the boundary conditions. For these two free regions, we find out the two different solutions. Now boundary conditions at x equals to 0. The delta functions, we already mentioned the delta functions at x equals to 0 impose a discontinuity in the derivative of the wave functions. Already we mentioned. For this delta potential at x equals to 0 impose the discontinuity in the derivative of the wave functions. That is already mentioned. This is already mentioned, right? This is already mentioned in the questions. So psi prime 0 plus minus psi prime first order derivative 0 minus is equals to 2m alpha upon h cut square psi of 0. Okay, psi of 0. Now let's find out for x greater than 0 regions, we have the wave function solutions psi of x equals to a e to the power ikx plus b e to the power minus ikx. Now at x equals to 0 plus, psi of 0 plus is equals to, let's put x equals to 0. Now solution is nothing but from this case psi of x equals to 0 plus, we get a e to the power 0 plus e to the power 0 plus a plus b. Similarly for its derivative, we have psi prime of x that is equals to a ik e to the power ikx minus b ik e to the power minus ikx. So that is equals to ik is common, a e to the power ikx minus b e to the power ikx. So at first order derivative at x equals to 0 plus, that is equals to ik a minus b. So this is the ik a minus b. Okay. Similarly, for another free regions, minus a greater than x, minus a less than x, less than 0, and for this case wave function is nothing but psi of x equals to c sine k x plus a. Okay, so for these regions we find out at x equals to 0 minus, x equals to 0 minus x equals to 0 minus psi of x equals to 0 minus, we get c sine of k and its derivative ck cos k. Okay, now we apply these boundary conditions at x equals to 0. Now I apply these boundary conditions at x equals to 0. These two so the first derivative, this is the value of this first derivative at x equals to 0 plus, and this is the value of first derivative at x equals to 0 minus. So this is equals to ik a minus b ck cos ka equals to 2m alpha h cut square upon a plus b, and a plus b is nothing but psi of x equals to 0 plus or x equals to 0. Okay, x equals to 0, x equals to 0 value. Okay, so this is equals to ik. So finally we get, now multiply it with a both side, multiply it with both side. So ika a minus b minus ckA cos ka into 2m alpha a upon h cut square a plus b, and here the given the constant beta equals to h cut square upon 2m alpha a and zeta equals to ka. Let's substitute these two value. So I zeta a minus zeta a minus b minus zeta c cos zeta equals to a plus b by beta, not beta by a, not beta by a. This is equals to only beta. Okay, this is equals to beta. Okay, so after boundary conditions we have a equations. After applying the boundary conditions, now reflections without phase shift. What is the meaning of reflections without phase shift? For no phase shift upon reflections, this means the wave functions at x equals to 0 must be real. No phase shift upon reflections, it means the wave functions for x greater than 0 must be real. This means the amplitude a and b must be continuous, must be equals, because this is real wave functions. So from this equations, from these equations, okay, from these equations, put b equals to a, here put b equals to a, then we get z minus zeta c cos zeta equals to 2a by beta, not beta a, beta, only beta. Okay, only beta. Okay, so that is because at the right hand side mention the wave reflected without phase change, so that's why we use this conditions also here, this boundary conditions. Now at x equals to 0, okay, at x equals to 0, psi of 0 is equals to a plus b, and that is equals to 2a, and psi of 0 minus is equals to c sine zeta. Why? Because we are already know at x greater than 0, psi of x equals to a e to the power ikx plus b to the power minus ikx. So from this case we find out x equals to 0 plus, so that is equals to obviously a plus b, but due to a equals to b, so equals to a plus a, so that is equals to 2a, And for another free regions minus a less than x less than 0, psi of x equals to c sin k x plus a. Okay, now put here x equals to 0 minus, that is equals to c sin ka, and ka is nothing but zeta, so c sin zeta. Okay, we get these two values, and these two values are continuous at x equals to 0, already mentioned in your questions, right? Already mentioned in your questions. Note that the presence of this delta functions per here, the derivative of the function is discontinuous at x equals to 0, and we already mentioned their wave functions at x equals to 0, psi of, so boundary conditions at x equals to 0, wave function must be continuous, so that is equals to x equals to 0 plus equals to x equals to 0 minus. Okay, they must be continuous. So after that we apply here the value. So c sin of zeta equals to 2a, so c equals to 2a upon sin of zeta. Okay, now substitute this value of c in the boundary conditions, in that boundary conditions. So finally we get zeta minus zeta 2a upon sin zeta into cos zeta equals to 2a upon cos beta, not beta a, beta. Okay, only 2 beta, 2a upon beta. So 2a cancel each others, so finally we get minus zeta cot zeta equals to 1 by beta, and that is equals to minus beta zeta equals to cot zeta equals to 1. So tan zeta equals to minus beta zeta. So this is the conditions, actually this is the tangential conditions we actually get. So we here actually one by one we apply the boundary conditions. So what are the boundary conditions? Actually there is two boundary conditions. First of all, we calculate the solutions of the Schrodinger equations for two free regions, and then we apply the boundary conditions. Okay, and then we find out the boundary conditions. The derivative is discontinuous and the wave function is continuous. At x equals to 0, their derivative is discontinuous, and this discontinuous value is already mentioned in your questions. Okay, this is the discontinuous value already mentioned in your questions. Okay, and also another boundary condition is at x equals to 0, the wave function must be continuous. We use these two boundary conditions and we finally find out the solutions. Okay, so please note down in the questions proper way. Okay, each and every solution is very important for your exam purpose, and please understand each and every concept in proper way. And if anyone feel any kind of doubt, I will definitely give the proper way to how to understand this type of questions. Okay, next we go to the question number 8. Okay, next we go to the question number 8. This is asked from kinetic theory of gas. The speed distributions of molecules of an ideal gas in equilibrium at inverse temperature beta equals to 1 upon kVt is found to be obey Maxwell distributions. This is the Maxwell distributions formula, Polar distributions formula, C v square exponential minus half beta m v square, where m is the mass of the molecule, c is the normalized constant. Compute the value of v to the power 4, expectations value of v to the power 4 whole to the power 1 upon 4. So actually they ask expectations value of v to the power 4 whole to the power 1 by 4. So first of all we calculate the expectations value of v to the power 4. So what is the so first we calculate the normalized constant, then we calculate the expectations value, and then the rest of the things. So the speed distributions of molecule is given as P of v equals to c v square exponential minus half beta mv square. We have the distributions must be normalized, so 0 to infinity where because v speed for speed have a integration, speed have a value 0 to infinity, that's why we use the integration limit 0 to infinity. Okay, speed is scalar number, so scalar number is no negative value, that's why we use here the integration limit 0 to infinity. Okay, so 0 to infinity p of v equals to p of v dv equals to 1, so p of v equals to c v square exponential minus half beta mv square dv equals to 1. Okay, so c now c integration c sorry 0 to infinity. So now let's put x equals to root under beta m upon 2 into v, so v square equals to 2x square upon beta m, and 2v dv equals to 4x dx upon beta m, so dv equals to root under 2 beta m root under 2 beta m into dx. Okay, now just substitute this value and we calculate the value of c is equals to beta m whole to the power 3 by 2 whole to the power root under 2 pi. Okay, you just calculate, this is very easy questions. Next we calculate the compute the v to the power 4 expectations value of v to the power 4, so that is equals to 0 to infinity v to the power 4 probability distribution functions and dv. So this is equals to v to the power 4 and we here put the probability distribution functions value, and now rearrange these expressions in one by one way, and we use here the gamma functions property. Okay, we use here gamma functions property. Okay, gamma functions property, and we get the value 15 root to the 15 root pi upon 8. You just calculate. Okay, you just calculate. So finally we get the expectations value of v to the power 4 whole to the power v to the power 4 expectation value whole to the power 1 by 4 is equal to root under 15 kb upon m. So this is the answer. So this is very easy, you just normalize these wave functions and then calculate it. Okay, this question is very easy. Next questions, question number 9. A classical particle undergoing simple harmonic motions is confined to a regions minus a to plus a on the x-axis. If a snapshot of particle is taken at random instant of time, what is the probability that it would be found in these regions a by 2 to a? So we know the simple harmonic motions probability distributions function. We first of all we calculate the simple harmonic motions probability distributions. Okay, so first of all we calculate simple harmonic motion probability distributions. We know that energy of a particle is given by energy of a simple harmonic particle equals to half m omega square x square plus half m omega square s square. A is the amplitude of oscillations. Okay, A is the amplitude of oscillations, right? Using the conservation of energy, we calculate the speed of the particle. This is class 12 problems. V of x equals to root under omega square s square minus x square. But we know for a classical particle undergoing a simple harmonic motions, the probability density at any positions x is inversely proportional to the particle speed. It's very important. Please remember this line. Okay, for a classical particle undergoing simple harmonic motions, the probability density at any positions x is inversely proportional to the particle speed. Okay, that is equals to p of x is equals to inversely proportional to the v of x. So that is equals to 1 minus 1 upon root under s square minus x square. Now normalize this distribution functions over the interval minus a to plus a. That is equals to p of x equals to 1 by z into 1 upon root under s square minus x square, where z is the normalized constant. Okay, normalized constant. We have put the value a equals to a actually amplitude. Okay, now find out the normalized constant, the value of z. Normalized constant value, integration limit minus a to plus a. Obviously its amplitude vary from minus a to plus a. That's why we take integration limit minus a to plus a. Minus a to plus a, p of x d of x equals to 1. So 1 by z minus a2 plus a 1 under root under a square minus x square d of x equals to a. This is the standard integrations and its a value always pi. You just calculate in x, take x equals to a cos a sin theta and easily you calculate the value. Okay, don't worry about that. This is very easy. So z equals to, we get z equals to pi. So we get the normalized constant value z equals to pi. So finally the probability distribution functions p of x equals to 1 upon pi 1 by root under a square minus x square. Okay, next calculate the probability in these regions a by 2 to a. So probability in this region is very easy. A by 2 to a, probability distribution function into dx, a by 2 to a 1 by pi into 1 by a square minus x square root under a square minus x square dx. So 1 by pi integration limit a by 2a, okay, root under a square minus x square. You just calculate this here, the value. So this is value equals to 1 by a sin theta minus a sin theta d theta. You just calculate, very easy. I calculate everything here. So that is equals to 1 by pi 0 to pi by 3 into 1 d theta, that is equals to pi by 3 into 1 by pi. So we finally get the probability equals to 1 by 3. So from this questions, so these questions are very easy questions. Okay, most of the time they questions asked from the probability distributions function. They give probability distributions functions and normalized it and calculate the probability at particular regions, right? We ask this kind of questions many times. Next, question number 10. The ratio of the molar specific heat of an ideal gas is given equals to gamma equals to Cp upon Cv equals to 3 by 2. It undergoes a reversible isothermal expansion in which volume is double. Okay. Next undergoes reversible isochoric, that is constant volume process, such that the change in entropy in the second process is equals to change in entropy of the first process. So what is the ratio of the final temperature to initial temperature? It is very easy. You just calculate the change in entropy for reversible isothermal process and reversible isochoric process. Okay, so change in entropy change in the isothermal process, it's a formula. Delta S 1 equals to nr ln Vf upon Vi. Vf is the final volume, Vi is the initial volume. So here Vf is equals to 2V and initial volume is equals to V. So change in entropy in isothermal process is equals to delta S1 equals to nr ln 2. Okay, this is very easy. So change in entropy in isochoric process, it's a always formula. Delta S2 is equals to N specific heat of Cv is ln Tf upon Ti. This is the final temperature and this is the initial temperature. So we know that these two entropy are actually equal. So delta S1 equals to delta S2. So nr ln 2 equals to Ncv ln Tf upon Ti. So Cv Rr cancel each other. Nn cancel each others. Okay. So Cv ln Tf upon Ti equals to R ln Z. We know Cv is equals to R upon gamma minus 1. We just substitute this here. R upon gamma minus 1 ln Tf upon Ti equals to R ln 2. Again Rr cancel each others. So ln Tf upon Ti upon gamma minus 1 equals to ln 2. So ln Tf upon Ti Tf upon Ti equals to gamma minus 1 ln 2. We just simplify this. So Tf upon Ti equals to 2 to the power gamma minus 1. So here given gamma equals to 3 by 2, already given in your questions, we just put here. So Tf upon Ti is equals to root 2. So finally final temperature to initial temperature ratio is equals to root 2. It's very easy problems. Okay, so okay, very good. Again this is again I post this PDF in my Facebook page in details solutions. If anyone till now following my page, please follow this page for access this kind of PDF and also the notes, various kinds of notes. Okay, so today's class is now end here because in today's class I discuss total 5 questions in details, one by one, step by step solutions method. Okay, and in the previous lectures also I discussed the question 1 to question 5 in detail, step by step solutions. Okay, if you are get the benefit from my channels, please subscribe and like my channels, because it's your responsibility to inspire me to make another video, this kinds of video. Okay. So okay. Okay, so again, thank you for watching this video. I will meet with you another videos for the last sections of part B with question 3. Okay, so thank you for watching this video.